Good morning, everyone. I am Chithra Lekha. We are from Virginia Tech, India. Virginia Tech, India is part of Virginia Tech, US. Here in Chennai, IIM Research Park, we have a research center. And also, we are part of two medical colleges where we do a lot of research and product development on medical devices. And we immerse the problems along with doctors, and we develop solutions for them. So today I'm going to present here some of our works we have done for the past 5 years and the challenges we faced throughout our journey. So we have developed a portable impedance-based microfluidic biofuel cell printed on cellulose substrate for enzymatic urea sensing. So in our team, when we started looking for solutions along with doctors, one of the problems came was the geriatric care. So in ICU patients, most of the time, as Dr. Ajay told, most of the time doctors are facing a lot of trouble when they go on checking for their patients' vitals and other parameters. So they want some kind of devices which go non-invasively and without the intervention of any professionals or duty doctors. They should be able to watch the disease progression or any kind of diseases. So or change in their vital condition. So in that case, one of the problem came was that the urea to creatinine ratio in geriatric care, especially most of the time when the dehydration happens, this delirium is one of the risk factor. And in ICU patient especially, they want to check this. And also other parameters also they want to check, but we started with this and we thought of developing this sensor. But once we started it, then only we found that there are other challenges also. Like whenever we develop some technology, it always has to face the sustainability. Since it creates a lot of electronic waste and a lot of menace landfill contamination, especially we go for a non-invasive thing, which is kind of sensor board. Then we thought that we should look into that factor also. And so taking into account of this scientific social responsibility, we are looking for solutions which can go hand in hand with the technology as well as sustainability. And that's how we started developing this. And I will tell our journey. These two challenges we took, and we have started working on two products. One is the flexible substrate, and on which, but that flexible substrate, what we look for is that it should be from green source. It should be biocompatible and biodegradable. Because even though we are using it as a non-invasive thing, it may be going to the skin, so it should be compatible. And then it should be printable with any kind of ink and with any kind of printing technology. So that's how we developed this Flexil, which is now the patent is filed. And it's actually from a waste, actually from a nutraceutical waste, and we developed it further. And now what we started working is from the waste, from the R&D to at the end of ditching it away, everything should be green. That's what we concentrated. But we know the challenges in that, because the reproducibility, as he said, everything is a challenge. Reproducibility should be there, scaling up should be there. So when it goes to as a product, we have to look for all kind of this kind of things. And so another product we developed is this e-ink. So this is the proof of concept for our Flexil, and the data sheet is shown here. We have done the thermal and mechanical properties as well as the biodegradability, biocompatibility. Sorry, it's not shown there. And even we have tested the contact angle and wettability, and we have printed various things on that, and we have checked how much compatible the substrate is towards various things like 2D materials or towards nanoparticle ink. And we found that our substrate what we developed in our lab is needs no curing before printing or post printing, and it goes well with any kind of printing, from screen printing to inkjet printing. and even with this extrusion printing, like 3D printing. So these are all our results, and then we have developed another ink. This is from coal. Actually, people are relying mostly on the graphite for making graphene, and we have developed this one-pot method, and we made this coal-derived graphene oxide, and now we have made the ink out of it. And this also we have tested at our lab, and here is our data sheet, and we have printed on that cellulose and other substrates also to check the printability, and even in PET also we have checked it. And with this, I am getting into the real problem we were addressing. So we tried it to construct a self-powered biosensor for biomarkers in urine, which goes to a urine bag in an ICU patient. So for this, we have made this architecture, and we have tested this for different concentration with the EAS. So we used enzymatic biosensing method, and urease was the enzyme we used. And right now we tested it for urea only. Later on, we are planning to move towards urea to creatinine ratio, because that is what people really want. And since this urea catalyzes the hydrolysis of urease is doing this, because of that, this mechanism is happening. So since our team is having a person, Suman, who is working on energy storage devices, and she is especially an energy specialist. She want to see an integrated system with integrating a fuel cell as well as a supercapacitor along with this biosensor, and tested functionality. So we have tested this also, and we found that there is a 40 times increase in the current output when we use this urea concentration. With increase in urea concentration, it has increased. So right now we are in the development process of this sensor, as well as we are looking for developing, attaching the electronic components also, so that it can be a standalone system. Thank you.